Okay, here is part 2 of lesson 9.3. So last time, guys, in part 1, we ended by talking about arithmetic sequences that were more of that linear pattern because they were always adding something to get the next term. So today we're going to take a look at geometric sequences, where now you are getting more into the exponential growth, because now the key word is you are always multiplying every time to get the next term. So as far as a quick vocab, common ratio, the common ratio is the number that you are multiplying every time to get the next term. So in this case, here's a super easy one for us to look at. We are obviously multiplying by 3 every time to get the next term in the sequence. So that would be our common ratio. I give you guys a little sort of formula approach to these guys in the last one as far as finding a common difference, because some patterns are much harder to identify what that commonality is depending on how they lay out the numbers. This one is very easy to see that I'm multiplying by 3, right? But what if I couldn't tell? All right, what if it was more complicated numbers? What if it was decimals, fractions, whatever, and I could not tell what they were multiplying by to get the next term? Well, again, just like the name suggests, a common ratio. Remember, ratio is a fraction, it's division. So the reason they call this the common ratio is because I can take any term, divide it by the previous term in order to get the common ratio, right? So it's like we're working backwards here. So I can take any term. Let's not write it that way. So in order to get my common ratio, which is r, I can simply take any term and divide it by the previous term in order to figure out that common ratio, right? So in this case, I could take 6 divided by 2. That would tell me my common ratio is 3. And that would work for any 2 consecutive terms, right? So in this case, we can see that it's 3. As far as finding the 10th term, there's a formula for that. So you can see formulas on this page. Let me just lay it out for you here. So as far as geometric sequences, we're taking the first term, that's a 1, multiplying it by the common ratio, and then raising it to the n minus 1 power. One thing I mentioned in the previous formula, the connection between a of n and n, don't ever lose sight of that. Remember that n represents the term number, so first term, second term, third term. A of n is the value of that term. So if I said, again in this case, that my third term is 18, that means when n is 3, the value is 18. So I always want to see that relationship within that formula. So if I wanted to find the 10th term, it's really just plugging in numbers. So pretty simple once you know the formula. So again, here's the layout of it. So they put the first term right there. Here's my common ratio. And then if I'm going to raise it to the n minus 1 power, well, if I'm looking for the 10th term, then I'm going to put in a 10 for n. And then it's just simplify that, clean that up to come out with this value. You are now talking about exponential growth, so you will see some much larger values in the geometric sequences than you were seeing in the arithmetic sequences. Guys, one simple math rule that I know you guys know, but just in terms of being careful with your algebra, remember when you look at this layout here, you cannot ever, ever, ever multiply those together without applying this first. Okay, so as I look at this right here, right, this was when they simplified the 10 minus 1, it became a power of 9. Keep in mind, you cannot multiply those together and say that it is 6 to the 9th power, right? You got to stick with PEMDAS. I have to do my exponents before I multiply times 2. So don't ever forget that. It's a common mistake, and I know you guys know the rules behind that, but just something to be aware of. As far as writing the recursive rule, again, we identify the first term and then say, okay, what am I doing to each term to get the next term? And it's simply multiplying them by 3. And so that's the way we would write the recursive rule for this. When it comes to writing the explicit rule, again, you're doing the exact same thing that you did right here with the formula, but you leave n as n. So when you want to write the explicit rule, you're going to put in for the first term, you're going to put in a common ratio, but leave n as n. So this one really won't simplify very much. Remember, that's as far as it goes. You cannot multiply those two numbers together because of the exponent. So this would be the explicit rule, and that's as simple as it can get. All right, let's look at one that's a little tougher. So in this case, again, if we're told that it is a geometric sequence, and I'm trying to figure out what my common ratio is, remember, I can always take any term divided by the previous term to figure that out. So if I did 2 to the 9th divided by 2 to the 6th, so it looks like this. Remember, you can't clean that up. These guys do have common bases. So your rules of exponents say that anytime you're dividing, you're allowed to subtract the exponents. So we could write this as 2 to the 3rd power, which is also 8. Right? So in other words, if I take any of these divided by the previous term, I should get 8 every single time. Or 2 to the 3rd. You could write it either way. Obviously, I think 8 would be a little simpler, but they kind of kept writing this as 2 to the 3rd. But anyway, beyond this, really no different than what we did in this first one. So let's come down here and do one of these together here for practice. So, again, first things first, if I want to find the common ratio, I can take any term divided by the previous term to get my common ratio. In this case, you can see that it would be -3 every time. So now if I want to find the 10th term, I'm just going to apply the formula that we saw up above. That says let's take the first term times the common ratio to the n-1 power, which is just going to look like this. And that's just something I would do in my calculator. You're going to do -3 to the 9th power, and then multiply that answer by 3, and you got your 10th term. As far as the recursive rule, again, for the recursive rule, you should always lay out the first term of the sequence, because then we are going to combo that with the recursive rule that says for any given term, I'm going to take the previous term and multiply it times -3. So that's the way I would write the recursive rule. Moving on down to finding the explicit rule, same thing that we did here, but you leave n as n. So for the explicit rule, we're going to say it is 3 times -3 to the n-1 power. And remember, you cannot simplify that. That's as simple as it gets. All right, let me flip over to the back page. Here's what we got. So this example is simply going to be a combination of an arithmetic idea and a geometric idea. So we're going to break this up into 2 parts here. So what they're telling us is we have this sequence. They're going to tell us the second term is 3. They're going to tell us the 5th term is 192. And they're going to say, okay, well, if that's an arithmetic pattern, then come up with a recursive and explicit rule for that. If it's a geometric pattern, same thing. Come up with explicit and recursive rules for that. So let's just start with the arithmetics. So one thing is we got to keep in mind is if I'm going to write an arithmetic rule, remember the 2 things I need to know is the first term and the common difference. Well, I don't know either one of those. All I know is a second term and a 5th term. So something we've talked about before is, well, if I have 2 unknowns, well, then I'm going to need 2 equations. And I'm going to have to solve a system of equations in order to come up with those 2 unknowns. Same thing is going to happen for this guy. In order to write a geometric rule, I need to know a first term and a common ratio. And again, we don't know either one of those yet, so I'm going to need 2 equations in order to solve that. Instead of taking you through their entire process, we're going to do just one of these of each together on our own, so that we can lay this out. But one thing I will mention is this. When it comes to arithmetics, remember that these are linear patterns. And so for these guys, we're going to need we can solve this using elimination. When it comes to geometric, we tend to solve those using substitution, not elimination. So that's kind of what we're going to be looking at as we go into these guys. So for this first one, we're looking at an arithmetic sequence. They're going to tell us what the third term and what the fifth term is. I'm going to take a slightly different approach than what they did up in their example right here because I want to relate this to something we've already done in solving systems of equations. So I'm hoping this will make a little more sense by taking this approach. So if my third term is -1, let me just write that out real quick. So my third term is -1, and they're telling me that my fifth term is 3. So if you consider the formula for arithmetics, it looks like this. So to write my first equation, I'm going to use this information. So if my third term is -1, that means when n is 3, my value is -1. So let me put those in. So if I have a 3 right there, obviously 3 minus 1 is 2. So I'm going to write that as 2d. So let's do the same thing with this guy. All right, so my fifth term is 3. So when n is 5, a of n is 3. So again, if I put a 5 right there, I know 5 minus 1 is 4. So I'm going to write that as 4d. And so there's my 2 basic equations. I can simply solve that system by elimination. I'm going to subtract everything straight down and let those a1s get eliminated. So if I did -1 minus 3, I get -4. These guys cancel. 2 minus 4 is -2d. Divide both sides by -2. And we got +2 is our common difference. And now that I know my common difference is 2, I could simply plug that back into either one of these in order to figure out my first term. So if I put a 2 right there and solve that equation, let's see, that would be 4, subtract the 4, and I get -5 as my first term. All right, so now I can write the recursive and explicit rules now that I know what these guys are. So remember, for the recursive rule, we identify the first term, which we've already done, and then I can say, I'll just put it over here, put it right down here below it. So now I can say that my pattern is to take any term, any previous term, and add 2 to it, since this is an arithmetic pattern, in order to get the next term. So there's my recursive rule. If I want to write the arithmetic rule, then we go right back to the formula right here. Just remember, for the arithmetic rule, we're going to put in a value for d, and for a1, we leave n as n. So I know it's my first term plus n minus 1 times my common difference. And it is good to clean that up as much as we can. So if I distribute the 2, I'm going to get a 2n minus 2, combine that with my -5, and I got -7. So there's the explicit, there's the recursive rules. So with this one, again, it was easiest to just set up this basic system and use elimination. It's a little tougher with the geometric pattern. You cannot use elimination when you're dealing in exponents. So when it comes to doing the geometric ones, I'm actually going to take their approach, because the substitution process, it's not a bad process, but I think there's process they show up here comes with a little less steps to it. So let me show you guys that one. So if I know the second term is 21, and I know that the fifth term is 567, as far as writing those in terms of the formula, so remember, our formula looks like this. All right, there's our formula. So let's plug in some numbers here. So when my second term is 21, means when n is 2, my value is 21. So if I'm going to put a 2 right there, obviously 2 minus 1 is 1, so this is going to be r to the first power. Let's do the same thing with that statement right there. And so we're going to say 567 So 5 minus 1 tells me to use a fourth power, so it's going to look like this. So you could use substitution on this. I could isolate a letter and then sub that information into the other formula, but I kind of like their approach on this. They basically set up a proportion. Because there is a common ratio, we're allowed to set up a proportion on this. So I'm going to set up this side. So A1, R4. So we're doing this guy over this one. So that's our first ratio, and that's going to have to match this ratio on the other side of 567 compared to 21. So we're just setting up a proportion because of the common ratio concept within a geometric pattern. From here, what they would do is they would say, well, let's reduce. These guys can cancel. Remember, if I have r to the fourth over r to the first, because they have a common base, I'm allowed to subtract their exponents. So it becomes r to the third. And on this side, if we did 567 divided by 21, we get 27. So it looks like this. Now I can simply cube root both sides to figure out my common ratio. It is 3. Just as a quick side note, if that was an even exponent and you had to take an even root of both sides, you do need to throw in a plus or minus right there in that situation. If my common ratio is 3, let's just plug that back into a nice easy formula to figure out what our first term is. So if I put a 3 right there and solve that equation, I'm going to figure out my first term is 7. And now we're right back into doing what we did here, which is a recursive rule. We've already identified the first term as 7. So my recursive rule is going to say that any term is equal to a previous term times 7. And as far as the explicit rule goes, just going back up to this formula right here, but we leave n as n. So I got my first term times my common ratio to the n minus 1 power. And that's it. That would be our explicit rule. Let me show you before we close out. I do want to show you guys something from your book on page 646. So if we really wanted to graph a sequence, really not that big a deal. All we're doing on that is we're just graphing the function. However, when it comes to terms of a sequence, they're always integers, right? Positive integers. We're going to have a first term, second term, third term, fourth term. So instead of this being a continuous graph, right, we're not seeing values in between points, right? We're only seeing integers for points. So this is my first term, second term, third term, fourth term, right? So I'm only looking at the values where x equals 1, 2, 3, 4, on and on and on, right? That's all we're going to see on that. So you're going to see basically points instead of a continuous curve. So this takes you through how to do this within your graphing calculator if you're using a graphing calculator. So if you are, you can take a look at it, the directions given right here for example 8. And they actually give you 2 different ways to do this. So you're welcome to look this over if you're going to use a graphing calculator. If you're going to use Desmos, then we got to look at the Desmos way of doing something like this, which there's functions within Desmos to do these graphs as well. And so you're going to kind of split off here at this point, and you can look up how to do this in Desmos if you want to use Desmos, or follow these directions if you want to see how to do this on a graphing calculator. With example 9, for these ones, we're actually looking at how do you get a sequence itself using a graphing calculator. So I'm going to show you both ways. So here's the explicit rule way of doing it. If they give you a recursive rule, then there's a separate way of looking at it. So let me flip over to this page real quick. So same idea. We're not going to use a ton of technology for this, so I'm kind of let you guys kind of look at this on your own. It's nothing more than just following directions that are given right here. So if you're using a graphing calculator, you just want to follow these directions and go through the process for what that would look like. Okay, and they're giving you both ways of doing it, whether it's explicit or recursive. So just take a look at those directions, and they're going to lay out the process for you on how to do that. There's one thing I wanted to show you guys. Something very, very common that you may have heard of before, which is something called the Fibonacci sequence. There is a very in-depth idea behind the Fibonacci sequence, something that they relate to all these patterns within nature and all this stuff, something called a golden ratio. Let me just quickly tell you the basics behind the Fibonacci sequence, which is the general rule of any term is always defined by the sum of the previous two terms. So if I took obviously two very basic numbers and said my first term is 1 and my second term is 1, well, that would make the third term 2, right? Because it would be the sum of the two previous terms. So let me just kind of lay it out like this. I'll put it over here in this empty space maybe. So if my first term is 1 and my second term is 1, well, if I add those together, I get my third term. Well, if I add the two previous terms, 1 plus 2, I get my next term. If I add these two terms together, I get the next one. If I add these two together, I get the next one, on and on and on. So that's how the Fibonacci sequence works. You're always getting a term by adding the two previous terms to get the next term. Obviously, in a case like this, in order to be able to get any term, they would have to start out by telling you what are the two previous terms, because I need to know what those are and add them together in order to get the next term. So the most basic Fibonacci sequence starts with a 1-1 beginning to it, and that way I can then continue on this pattern of adding the two previous terms to get the next term. But that's the pattern behind the Fibonacci sequence. So if you really wanted to look further into this, take a look at the Fibonacci sequence. You can look up something called the golden ratio, and how there's a very interesting pattern in nature that relates back to the Fibonacci sequence, but I'm not going to go into depth on that right now. We're gonna call that good for section 9.3.